All right. So let's get into our guest speaker segment. Pretty excited about this conversation, also because Kelly McCann is going to be conducting our interview, which is great to kind of have her on stage instead of just giving us updates on PD and events. But let's welcome Dr. Pavalkis to the stage. He is an MBSE Transformation Leader and MBSE R&D Cyber Portfolio Manager. In fact, all of your credentials were very long, trying to get that into just a paragraph on the screen. He is going to be a speaker as well at AeroTech, so I understand that you're going to be touching on that as well, right, Kelly? Okay.
Yes, excellent. Yes, we will be. Thank you so much, Dr. Pavalkis, for joining us. Can everyone hear me okay? All right.
Hello, Angela. Hello, Kelly. Thank you for having me.
Yes, thanks for joining. And it's my understanding this is not your first time presenting on an SAE webinar. I think you work very closely with Leslie McKay and have been on a few SAE webinars in the past. Is that right?
That mostly was in relation with INCOSE, International Council for System Engineering, but together with SAE.
Wonderful. So let's jump right in. So can you tell us about your experience with MBSC, and for those on the call that might not be familiar, model-based systems engineering, and how you got involved in this field?
It was actually 20 years ago. I was just finishing my master thesis and was looking for work in my area, and I found that a company is looking for the experts actually on quality assurance. That was like the entry type of job. And that's how I started with a small company, No Magic, which ended up bought by the SOS system, which is actually now the leader in model-based system engineering using SystemL, System Engineering Language Standard. And from quality assurance, just took 1 year to go to analyst department and 10 years as an analyst product owner, building major capabilities. Went to the solutions and consulting department and now leading MBSE transformation globally and also representing R&D in the US market.
That's great.
Also, I could mention that I have PhD in model squaring, which is actually all completely implemented in the product, still quite unique capability, and also a couple of awards and certifications from system engineering professional from INCOSE, which we actively participate to educate and also to learn from system engineering professionals.
That's great. So a long time in the field. So for those that might not be familiar, how does MBSC differ from traditional systems engineering approaches?
Yeah, MBSC, model-based systems engineering, differs from traditional system engineering approach in several key ways. So first of all, emphasis on the models. In traditional system engineering approaches, system designs are typically documented in text-based specification, which can be difficult to read and to interpret. MBSC, on the other hand, models to describe and analyze system designs. These models can be visual, graphical, mathematical, providing a more intuitive and concise representations of the system. And one of the key things is the descriptive model. We can use analysis models every day, and that is done in text-based and document-based system engineering. But analysis models does not connect each to another. So we need descriptive model, which would be like 3D CAD in similar way as 3D CAD, not 3D CAD itself, but the same as 3D CAD describes the actual part, same system descriptive model describes the actual system from the functional perspective, from the logical parts perspective of physical parts, and interfaces perspective and characteristics perspective, to describe it, not to analyze, just to describe in the model. And then we can use other models to tie together to provide this architectural description, to do trade study and to evaluate performance characteristics using analysis models. So this is glue, that descriptive model, that's the key. And it is not the only part of the models in MBSC, but that's the key part of MBSC, because otherwise we will just have analysis models, which we had for years, which will not remove us from document-based. And a few other things about MBSC is that it is integrated approach, right? So it allows to integrate data because it's model-based. So it is semantically rich data. We understand what is that data based on standards. Again, we can interpret the data with the help of machines, so we can integrate them. Then collaborate, right? Because models is easy to read, easy to transition to different complexity, like maybe less details for the roles which don't need the system engineering experience to understand the project, right? Like project managers. And and then iterative approach. It is easier on models to work step by step, introducing new functions. And then automation, that's the key thing, because in all cases, digital engineering introduces huge automation gains, and that's the key of MBSE also.
So I think that's a really nice transition into the next question that I had regarding the benefits of using digital standards in MBSE. So are there, any potential challenges and limitations of using digital standards in MBSE, and what do you see as the benefits of digital standards?
Absolutely. So there are several benefits. So improve interoperability, as we discussed, model-based. So you can actually read by machine, by actually tools, instead of like, non-structured documents, which no one knows what is inside, right? And also that ensures that the different softwares vendors will be able to interchange the digital standards. It's increased consistency, right? So we can then read that material in concise way. Better traceability. So for example, if the standard is in digital manner, so we can change one part of the standard and know what it affects in other standards, because there's a lot of cross-references without saying that the whole standard is affected. No, just one part is affected. And especially if it is like related to the model of the system which the standard describes, then we know what is exactly affected in that model of the system which standard describes. Then actual systems like planes, cars, knows what is actually affecting in the new release of the standard, which is actually huge work to do if there is just regular standard change without saying what exactly is affecting. And then cost savings, right? As always, digital decreases the cost. However, there are some challenges. So learning curve, right? You need to learn language. Each discipline has its own language, like for example, SystemL, system engineering modeling language, which could be 10 times more popular than other languages for system engineering, but still it's new language to describe the systems. And there are other type of learning curve challenges like tools and so, and then compatibility, because there are few standards, so there's few implementations of the standard. The good thing is that SystemL is quite popular, so then we can stick to the popular standards and then interchange the data much easier compared to actually creating those transitions and integrations to be able to change between different tool implementations of the model-based language. Then maintenance, so someone needs to maintain still the models, still the standards, right? Even if they are in digital world, right? And then standardization, right? There may be challenges associated with standardizing digital standards across different organizations or industries, particularly when it comes to ensuring interoperability between different tools and models. This is like a kind of political sometimes.
Sure. Sure, and I know we're going to jump into the SystemL a little bit later in the interview, but in terms of practical examples, do you have any examples that you can provide about how MBSE has helped to expedite product design or uncover issues earlier?
We also were part of many of those cases. For example, one of the main areas is that the issues are discovered in early stage. And one of the cases is by Boeing 787 Dreamliner. Is a prime example of how MBSE can help expedite product design. Boeing used an MBSE approach to design and develop the 787 Dreamliner, which allowed them to complete the design in less time and with fewer errors compared to the previous aircraft designs. For example, using MBSE, Boeing was able to identify major issues with power distribution system early in the design process, allowing them to make the necessary changes before product began. This helped to avoid costly changes and recalls. Also, NASA is pretty much using on multiple projects, maybe almost on all missions, MBSE for years. One of those are Mars Science Laboratory. MBSC was also used in the development of Curiosity rover and other missions, like the one which is forgot the name of the mission. But in any case, in most cases, we can actually identify the pattern that we automate and identify issues in early stage. And for example, with one of the missions at the NASA, there was like even code auto-generated from the model for the key states of the mission. Like rover had 150 states, and we can generate code for those states in order to avoid deadlocks in each of the state. And also the mission had like 50 states. And that gives us like clarity to the actual running code, which would not introduce some unexpected, transitions from one state to another state. Like, for example, firing engines when we are on the ground instead of firing engines above the ground to stop the, landing rover. And there are many others, like Lockheed Martin submarines program and a few others which identify the early stage gains. When identifying the issue at the early stage, gains are like enormous because you can fix quickly problems.
No, that's wonderful. And I think it aligns very, very closely with SAE's mission in terms of safety and mobility. And I know this was not a planned, but I think the examples that you gave just really showcase why this is such an important element to the future and the development and the focus on safety. So can you share your thoughts on the future of MBSC and how it will impact systems engineering the next, call it 5 to 10 years?
Yeah, model-based system engineering has been gaining momentum in the past few years, and is expected to continue to be an important part of the system engineering in the future. In the next 5-10 years, I believe MBSC will impact system engineering in the following ways. It will be definitely increase adoption. Many organizations are just starting adoption. In some domains, they are still doing pathfinding projects, but that is increasing every year. We see the enormous growth every year. And one of the digital engineering paths is like MBSC in most organizations. We can almost say that for sure. But still, their organization-wide adoption is not yet present in most of them. So this will continue. Improved collaboration, right? MBSC will provide a standardized description of the system, right? So that will improve collaboration with other tools, analysis tools. There are thousands of analysis tools, even owned by some organizations, like defense contractors. So we want to get the architecture data automated way for those analysis tools. So that's definitely is the path to go, to provide that, not human putting the data, introducing errors. Even the human is the best in that area, but still can be introduced errors. And enhanced automation, again, like integrations and data visualization and analysis, and up to the transition to the manufacturing and virtual testing and all of that, right? Even we do testing on virtual environment, we still need system engineering to introduce the changes to virtual environment, introduce new functions. There's no difference how we make the system. Is it virtual? Is it real? Still, there is like system engineering involved, and MBSC gives that automated approach. More advanced products definitely will be new products, and we'll talk a little bit later about SystemL 2, which is coming, and we are going to support it. And that's again, big jump forward with the standard, but also with the more advanced products. And one of the most important things is the greater use of AI. As more data is generated from BSC, I expect to see greater use of artificial intelligence and machine learning techniques to analyze and optimize system models. This will help engineers identify potential problems before they occur and make more informed decisions about design and development of the system. So we can say initially that it will not be like, for example, AI will design the system, but soon will suggest what would be the options for the designers not to miss some stuff. And that will come quite quickly unfortunately, the domain moves not very quickly, so maybe 5-10 years.
Sure. So why do you think it's important for aerospace OEMs? I know you had mentioned a few of the projects that you're currently working on, but specific to the aerospace OEMs to leverage MBSE?
Aerospace original equipment face challenges in the design of development of complex systems. So complex is the key here, right? Including the need to meet the demanding performance requirements, comply with safety regulations, and keep development costs and schedules under control. And the MBSC exactly can help aerospace OEMs to address these challenges in several ways. Improve collaboration, right? So this is with the partners, with the clients. Increase efficiency by automating tasks, right? So MBSC definitely does that with the ability to apply digital engineering in system engineering domain. Enhance accuracy, right? So we can now identify problems faster and be more accurate. Also, we can track the system requirements implemented correctly, not miss the requirements implementation, be on track on those requirements implementation, in order that we would take a decision when and what to cut if we have the budgets and if we need to increase the project, not by accident discovering at the last stage. Better decision making, that's exactly what we want to have in control, that we would track project status. More informative decisions, because we will see in the models things what we can't sometimes find in the 1,000 pages of document easily, just better visibility. And one of the main things is regulatory compliance. Aerospace OEMs must comply with a range of safety and environmental regulations, and MBSC can help ensure that regulatory requirements are properly captured and integrated into the system design. This can help reduce risk of regulatory non-compliance and improve system safety. And there's no better way to do it when you have an actual physical trace from requirement in repository to the system architecture which got implemented.
Great. Yes, Dr. Pavalkis, I find myself on no less than 2 flights a week as of lately. So the proactive approach and knowing that the safety and the testing of this is a top priority is very reassuring as a consumer and commercial flyer. So thank you for that background and information and all the work you're doing in this space. So pivoting just a little before we wrap up, you've mentioned SystemL a few times within the interview. So what role does SystemL play in the context of MBSC, and what are the benefits that you can speak to of version 2?
Yeah, thank you for that question. Because it's key standard, again, because it describes the system as a descriptive language, right? It's not really intended initially or in general for analysis purposes, but it describes them. And then as a standard, it is quite recognized and gives ability to agree on the implementations, interfaces, which allows us to interchange with the other tools. It's general modeling language for systems and plays key role in MBSC. SystemL is designed specifically for modeling systems and their associated behavior, structures, functions, interfaces, characteristics. And that's the key thing, because those are the things which we describe when we describe the system architecture, right? What it does, what part does it have, like logically, for example, heating, cooling, fuel system, propulsion and control system, right? And then also interfaces, because we outsource parts of the system complex, especially like engine is outsourced, right? So we need to define interfaces, and that's what actually SystemL does. And then also characteristics, like performance characteristics, like weight and fuel flow and so on. It provides graphical symbols, like graphical diagrams, but also provides the language semantics behind that, right? So It includes requirements, architecture, behavior, physical components. And it's quite mature already. It is started in 2006, so now it's like 2023, and we are about to have second version, which will be revolution on SystemL 2, right? There's a lot of companies and experts working. That's another advantage, to have like a recognized standard, because all community contributes, not only vendors, to SystemL 2 language. And what it will improve, SystemL version 2, it improve usability, will be easier to learn, easier to model, because we learned from SystemL 1 a lot, enhance capabilities, modeling complex systems, including support for multi-physics, multi-scale, and multi-domain modeling, formal semantics, so it will no longer be semi-formal. So what it means, semi-formal, it will be complete formal, so the text behind the language will be interpreted, and you can put the text and that transitions to model, and you can put model that transitions to text. And that actually introduces the next step is the model portability, because when you have text-based language, you can easier merge, you can easier, configure a control, which is very important for new type of systems, software-based systems, which is actually the thing which increases complexity in the systems, in most cases, software-based. And they need to be produced in agile method. And agile method is very related to software, right? And the software is actually managed in the text-based environment. So we are good at model management and software management. On top of that, we'll introduce agile in MBSC, model-based system engineering, with help of SystemL 2. There will be a lot of that kind of systems. And then extension mechanisms, there's actually formally defined interfaces to extend SystemL 2 for, again, interchanging with the design, like libraries for 3D CAD and analysis tools.
Sounds like there's a lot of work being done to move to that V2. So
yes,
thank you for that information.
Yeah, it's still in work, actually. Still, we have 1 year to final release, and it's very promising. We can already see what's happening, and almost final, but still work in progress. Great
to hear, and thank you for the update. So to wrap up, and we'll open it up to any questions. I'll check the chat here. But before we wrap up the interview, so you'll be speaking next month at our AeroTech event coming up in Fort Worth, March 14th through the 16th. So can you give us just a brief overview of what you'll be covering in your discussion at the AeroTech event coming up next month?
Yes, so I personally will cover value of digital standards, and will demonstrate some models together with SAE International, Leslie McKay, and Alexander Jackson from NOLA. And also we will do deep dive into the end-to-end model-based digital engineering certification from MBSC to design, where we will show actually a practical sample going from the requirements to system architecture to the 3D design, mechanical design, and then validation and verification. And also there will be a couple of panels on digital engineering in the MBSC perspective, and insights from government and industry. And also there will be participation by NASA on the standardization in the area of VTOL. Then will be also Lockheed Martin talking about performing functional analysis to analyze customer requirements, and few other participants. Those will be 2 very busy days of MBSC and relating to digital standards.
Great. Well, we look forward to having you there in person. For anyone that's interested, registration is still open, so please join us at AeroTech. I'll be there on site at the SAE booth. It does look like we have a few questions in the chat here. So we have a question from Saad Aldin saying, is the V cycle considered an example of MBSE methods?
So V is not really related to how you implement system engineering. You can implement in paper-based, document-based, or model-based, right? This is like technique, how you do like how you describe your system, right? Are you describing it each time you do like system engineering task in the paper? Like, for example, safety analysis, right? So to do safety analysis, you need to know functions which you analyze, right? Like, and more than that, right? So do you start from the list of functions, or do you take the model and then perform that, right? So it's still the cycle is the same. The system engineering is performed, all tasks are the same, but in the digital method, which is enabled with model-based system engineering, you are actually contributing to the same system architecture project, like functions. If you do the safety analysis, you take those functions which are identified by architect, and you perform safety analysis. And then once you identify that some of the requirements needs to be updated or new introduced to mitigate critical safety issues, you pretty much introduce them, and then they need to be satisfied by architectural changes. So you have that whole cycle in the same project with the consistency, and nothing is missing.
Thank you so much for that. And we have one more question that I see in the chat here. This is from Oliver, and he is asking, are models in MBSC limited to describe requirements and specs, or do models play also a role in the validation part? If you could address that.
So they do play, because when you describe, like, for example, if you do validation against requirements, right? Verification and validation, like in the actual system engineering. So it doesn't matter, is it model-based or document-based. So if you have your requirements of system architecture in the model, right? So you know that system needs to perform those functions, those interfaces should be supported, those characteristics those supported. So then you run the validation. Let's start with the verification, which is the testing your system architecture, right? It's actually a verification test, right? Testing your system architecture. Your architecture is implemented correctly, right? That's what is verification. So you can run digital tests, which would allow you to automate that process, which would not be possible even if your requirements are in the document, right? Because now you can interpret your system, you can test interface, you can run the protocol test, and so on. The validation, so you actually accept the system, that system is actually does what is expected from the user, not from the requirements. So that's quite user-oriented, but because we have digital description of the system in MBSC model-based system, right? System engineering, right? We can do that validation at the beginning. So we could save all the V-cycle, all the implementation, and run that by simulating the project system in the model from the use case functions perspective, and show the user, do you really want that system would behave in that way? Before actually building even system architecture, we can just describe the use cases and run the simulation, and then continue running it together with the user to test all the different scenarios which needs to be implemented in virtual environment, even before designing the system. So that definitely helps, because if we'll run the final validation with the user on final product, so we might get like negative feedback at the end, and that will cost us a lot.
Thank you so much for addressing those questions. I don't see anything else in the chat, so very much appreciate you jumping on with us today for the webinar, and we're looking forward to having you in person here next month at AeroTech, which this is a nice transition into my next segment here as we wrap up promoting the AeroTech event. Thank you, Angela.